Hi everyone. Today we'll be analyzing the flexural stresses in leaf springs. Leaf springs consist of a curved bending beam that bends in response to force from the wheel to absorb shocks. Leaf springs are the oldest type of suspension and were even used in chariots thousands of years ago. Because of their simplicity and robustness, they're still used today in a lot of heavy vehicles like trains and trucks. What we're going to talk about today is why leaf springs have this design where they have multiple leaves that are each a little shorter than the last one. We're going to analyze the flexural stresses in the leaf springs. If you're using the Mechanics of Materials textbook by Craig and Taylor, this content is in section 6.3. As a brief overview, when we have a transverse force applied to a beam, or when we have a moment applied to a beam, reaction moments are generated within the beam that usually depend on the location, in this case our position x. These reaction moments create normal stresses along the direction of the beam, which is the x-axis in this case. These normal stresses that are created by a moment are called flexural stresses and can be calculated using our equation that states that the magnitude of our flexural stress is equal to the moment times the distance from the neutral plane in the y direction divided by the second area moment. The second area moment is a geometric property of the beam cross-section, and for a rectangle, the second area moment is given by the width of the beam times the height of the beam to the exponent 3 divided by 12. Notice that the distance from the neutral plane and the second area moment are both based on the geometry and don't have any terms related to the real leaf springs are curved, but we'll draw our leaf spring as being straight. And we're going to look at an example leaf spring that has two leaves, with the second leaf being half the length of the first leaf. The leaf spring is supported on both ends like a simply supported beam and has a force applied in the middle from the wheel. We can see from the drawing that this system is symmetric, so we're going to analyze this by only looking at half the beam, using something called a constrained rotation end at the middle of the beam. This constrained rotation end indicates that the beam is free to move up and down at that location, but it's constrained to have no change in the angle. If we draw the beam deflection that we would expect for this type of a system, we can see that if it's symmetric, the angle of the beam right in the middle will be 0, which is exactly the condition that's indicated by our constrained rotation end and why we can use it to approximate symmetric systems. A constrained rotation end has no reaction force in the y direction, but it does have a reaction moment because we're constraining the angle. This constrained rotation end is a boundary condition Now that we've determined the equation for the moment throughout the beam, we can start to look at the flexural stresses. We're going to compare two different conditions, one in which we have only one leaf and one where we have two leaves. In the first case, we can look at our equation for flexural stress and substitute in our equation that we've gotten for our moment. The largest flexural stress at a particular location x will be at the largest value of y, the distance from the neutral plane. And we'll call this the maximum flexural stress at position x. In the case of a rectangular beam cross-section, the flexural stress at the top and bottom of the beam have the same magnitude but different signs. At both the top and bottom of the beam, the distance from the neutral plane is half the thickness of the beam, giving h/2. We can also sub in our equation for 1 over the second area moment and simplify to give a final equation that's linear in x, indicating that the largest flexural stress at any location is at C in the middle of the beam. Lastly, we can sub in x equals to L/2 to find this value of the maximum flexural stress. In the leaf spring with two leaves, we can look at what's going on in the two different sections. The first section from x is 0 to L/4 is the same as for the leaf spring with a single leaf, with the difference that the maximum flexural stress is at L/4, which means it has a value that's half of the value than what we found at L/2. There are larger differences when we start to look at what's happening in the section when x is between L/4 and L/2. In this section, the beam is twice as thick, so the y value, or the distance from the neutral plane, doubles from h/2 to h. Since the beam is now twice as thick, it also changes our second area moment, and the term for the beam thickness is to the exponent 3, which has a very large effect on decreasing the magnitude of the flexural stress. So we've doubled a linear term in the numerator, but also doubled a cubed term in the denominator, which gives us a 2 squared term in the denominator. This gives us a line that has 1/4 of the slope, as in the first section, but is valid in the region from L/4 to L/2. When we work out the numbers for the stresses at the ends of the section, we can find that the stresses are much lower. When we compare the leaf springs with 1 and 2 leaves, we can see that the beam with 2 leaves has a maximum flexural stress that's half the value of the beam with 1 leaf. This is why leaf springs have multiple leaves that are in the middle of the beam. It reduces the flexural stresses and allows the leaf spring to carry more weight. In our case, we kind of arbitrarily chose the second leaf to be half the length of the first leaf because it's easy to work with fractions of 1/2. However, we can see that that was probably not ideal because we still have a stress concentration in the first section that's a lot larger than in the second section. So one thing that we might look into is what are the ideal lengths of the leaves of a leaf spring that would provide a situation where the maximum flexural stresses in each section are the same. In other words, how could we design the lengths of the leaves so that the flexural stress in each section are equal? Lastly, we always want to think about the assumptions we've made and how they might affect our results. Our first assumption was that leaf springs are straight, which we know is definitely not true. Leaf springs are actually curved, so how would this curve affect the reaction moment inside the beam? If we look at a simple free body diagram, we can see that the force and distance are the same. So we'd expect that the moment in the beam is actually about the same, whether it's curved or whether it's straight. So this assumption actually has relatively minimal effect on the calculations. But that raises the question of, if the curvature has little effect on the stresses, then why is it curved at all? Well, it actually has more to do with optimizing the displacement when a force is applied, which is a topic that's covered in a subsequent chapter on beam displacement. The next thing we can briefly comment on is our observation that we have a discontinuity in the flexural stress where we have a change in the thickness. In reality, it's very rare to have a real discontinuity in stress, and the actual stress distribution is probably a little bit smoother. This is something that we could analyze using an approach like finite element simulations. So in summary, we've looked at leaf springs as an example of beam stresses, because leaf springs, although they are very old technology, they're still very commonly used in heavy vehicles. We used a constrained rotation end to simplify a symmetric system, even though our system was already pretty simple to start with. We looked at how flexural stress depends on the cross-section geometry, and we saw that this is actually why leaf springs are designed to have progressively larger cross-section geometry as you go closer towards the middle of the beam, because that's where the largest moment is.